Welcome to this coding problem walkthrough. Today, we'll be solving LeetCode problem number 1200, titled Minimum Absolute Difference. This problem challenges us to identify pairs of elements in an array with the smallest absolute difference. We'll explore the intuition, approaches, and optimizations to solve this efficiently. Let's dive in. In this problem, you're given an array of distinct integers, and the goal is to find all pairs of elements that have the minimum absolute difference between them. For example, if two numbers in the array are close to each other, their absolute difference will be small. A pair, represented as A, B, is valid if both numbers are present in the array. The first number is smaller than the second, and their absolute difference is equal to the smallest difference possible among all pairs in the array. The output should be a list of these pairs, with each pair sorted in ascending order. Additionally, the entire list of pairs should also be sorted by their first elements, and if two pairs have the same first element, then by their second elements. This ensures the output is structured and easy to interpret. Let's look at an example to understand this better. Suppose the input array is 4, 2, 1, 3. First, we sort the array, which gives us 1, 2, 3, 4. Then, we calculate the absolute differences between adjacent elements in the sorted array. For example, the difference between 1 and 2 is 1, between 2 and 3 is also 1, and between 3 and 4 is 1. The minimum absolute difference here is 1. Now, we find all pairs of elements that have this difference. These pairs are 1, 2, 2, 3, and 3, 4. These pairs are then returned as the output in a sorted list. In another example, the input array is 1, 3, 6, 10, 15. After sorting, the array becomes 1, 3, 6, 10, 15. Calculating the absolute differences between adjacent elements, we get 2 between 1 and 3, 3 between 3 and 6, 4 between 6 and 10, and 5 between 10 and 15. Here, the minimum absolute difference is 2. Among all adjacent pairs, only one pair has this difference, 1, 3, hence, the output for this example is 1, 3. Now, consider the input array, 3, 8, minus 10, 23, 19, minus 4, minus 14, 27. After sorting, the array becomes 14, minus 10, minus 4, 3, 8, 19, 23, 27. Calculating the absolute differences, we find 4 between minus 14 and minus 10, 6 between minus 10 and minus 4, 7 between minus 4 and 3, 5 between 3 and 8, 11 between 8 and 19, 4 between 19 and 23, and 4 between 23 and 27. The minimum absolute difference here is 4. The pairs with this difference are 14, minus 10, 19, 23, and 23, 27. These pairs are returned as the output, sorted in ascending order. To summarize the constraints and edge cases, the minimum absolute difference is calculated between adjacent elements after sorting the input array. The constraints specify that the array size can range from 2 to 10 to the power of 5, and the integers in the array can range from minus 10 to the power of 6 to 10 to the power of 6. Since all elements are distinct, there are no duplicate values to handle. In edge cases, such as when the array contains only two elements, the result is straightforward as there is only one pair. Additionally, the array may include a mix of negative and positive numbers, but sorting ensures the differences are calculated correctly. For very large arrays, efficiency becomes critical. Sorting the array is key to solving this problem efficiently, as it takes O and log n time. Once sorted, a single pass through the array to calculate differences and identify pairs ensures the solution is computationally efficient. This approach ensures that even for the largest allowed input size, the problem can be solved within a reasonable time frame. To solve this problem, let's first consider the brute force approach. The idea here is to calculate the absolute difference between every possible pair of elements in the array. For each pair, we compute the absolute difference and keep track of the smallest difference we encounter. Once we know the minimum absolute difference, we collect all pairs of elements that have this same difference. The process involves iterating through all possible pairs, calculating the difference for each pair, and updating our results accordingly. However, this method requires two nested loops to go through all pairs, resulting in a time complexity of O(n squared). This quadratic growth makes it computationally expensive for large input sizes. Additionally, while the space complexity for computation is minimal, we still need extra space to store the pairs with the smallest difference, which depends on the number of such pairs in the array. The brute force approach has a significant drawback: it doesn't scale well for large arrays. When the size of the array approaches 10,000 or more, the quadratic time complexity becomes prohibitive. To address this inefficiency, we can use an optimized approach based on sorting. The key insight here is that for a sorted array, the minimum absolute difference will always be found between two adjacent elements. This is because sorting arranges the numbers in increasing order, ensuring that the gap between consecutive elements is smaller than the gaps between non-adjacent elements. To implement this, we first sort the array in ascending order. Then, we make a single pass through the sorted array, calculating the absolute difference between consecutive elements. By tracking the smallest difference during this pass and collecting all adjacent pairs that match it, we achieve the desired result far more efficiently than with brute force. Now, let's analyze the complexity of the sorting-based approach. Sorting the array dominates the time complexity, which is O, n log n. After sorting, we only need a single linear scan to compute the differences between consecutive elements, which adds an O, n, component. This makes the overall complexity O, n log n. In terms of space, we only need storage for the result pairs, which depends on the number of valid pairs, denoted as k. This approach is highly advantageous compared to brute force. Sorting simplifies the problem to a manageable linear scan, allowing it to handle large inputs efficiently. Though there are alternative methods, such as using buckets to narrow comparisons, these are less intuitive and unnecessary for this problem. Given the constraints and the distinct nature of the array, sorting remains the most practical and efficient choice. Given the trade-offs, the sorting-based approach is the clear choice for this problem. By reducing the complexity from O, n squared, to O, n log n, it becomes suitable for handling large arrays while maintaining simplicity and clarity. Sorting the array allows us to focus only on consecutive elements, minimizing computational overhead and ensuring correctness. A key observation here is that the distinct nature of the array eliminates the need to handle duplicate values, simplifying the logic for collecting pairs. While sorting does incur a cost of O, n log n, this is far more efficient than the brute force alternative. The sorting-based approach strikes a balance between efficiency and ease of implementation, making it not only optimal but also intuitive. This strategy takes full advantage of the problem's structure and constraints, ensuring a robust and elegant solution. In this problem, we are tasked with finding all pairs of elements in an integer array that have the minimum absolute difference. These pairs should be returned in ascending order, and within each pair, the first number should be smaller than the second. To solve this efficiently, we start by sorting the array. Sorting ensures that the smallest absolute differences are always between consecutive elements, which eliminates the need to compare every possible pair. This optimization significantly reduces the computational overhead. Sorting the array takes O, n asterisk log n, making it the most time-consuming part of our solution. After sorting, we initialize two key variables, an empty list result to store the resulting pairs, and a variable min_diff set to infinity. The purpose of min_diff is to keep track of the smallest difference encountered so far, while result will dynamically store the pairs that match this minimum difference. These initial steps prepare us for an efficient traversal of the array. After sorting the array and initializing the required variables, the next step is to traverse the array to calculate absolute differences between consecutive elements. We loop from the first index to the second to last index, comparing each element with the next one. For every pair, we calculate their absolute difference. If this difference is smaller than the current min_diff, we update min_diff to this new value, clear the result list, and add the current pair to result. This ensures that only pairs with the smallest difference are stored. If the difference matches the current min_diff, we simply append the pair to result without clearing it, as it shares the same minimum difference. This process ensures we efficiently identify all pairs with the smallest absolute difference by focusing only on consecutive elements in the sorted array. Finally, we return the result list, which contains all valid pairs in ascending order. Sorting the array initially guarantees that these pairs will already be in the correct order. There are several key insights that make this algorithm both efficient and robust. First, sorting the array significantly reduces the complexity of the problem. Instead of comparing all possible pairs, which would take n squared time, sorting allows us to focus only on consecutive elements, leading to a much faster solution. Second, after sorting, the traversal to find the pairs is a straightforward linear pass through the array, which takes n time. This makes the sorting step the dominant factor in the overall time complexity. Third, the algorithm handles ties seamlessly. By maintaining the result list dynamically, we can easily store multiple pairs that share the same minimum difference. Finally, the algorithm gracefully handles edge cases. For example, if the array has only 2 elements, the single pair is directly returned. Similarly, arrays with repeated elements, such as 1, 1, 1, are handled correctly because the minimum difference remains consistent. The use of simple data structures like arrays and scalar variables keeps the implementation both efficient and easy to understand. Let's analyze the time and space complexity of this algorithm. The sorting step takes n*log n, which is the most computationally expensive part. The subsequent traversal to calculate differences and identify pairs is linear, taking n. Therefore, the overall time complexity of the algorithm is n*log n. In terms of space complexity, the algorithm uses 1 additional space beyond the input and output arrays. While the result list grows to store the valid pairs, this is part of the output and doesn't count as extra space usage. To solidify our understanding, let's walk through an example. Given the input array 4, 2, 1, 3, we start by sorting it to get 1, 2, 3, 4. We initialize result as an empty list and min_diff as infinity. As we iterate, the difference between 1 and 2 is 1, so we update min_diff and add 1, 2 to result. The difference between 2 and 3 is also 1, which matches min_diff, so we append 2, 3. Similarly, the difference between 3 and 4 matches, so we append 3, 4. The final result is 1, 2, 2, 3, 3, 4. For an edge case like 1, 1, 1, the sorted array remains the same, and all pairs have a difference of 0, resulting in 1, 1, 1, 1. Another edge case to consider is when the array consists of only 2 elements, such as 10, 5. After sorting, the array becomes 5, 10. Since there is only one pair, 5, 10, it is directly returned as the result. This example highlights the simplicity of the algorithm in handling small inputs. The sorting step ensures the pair is in ascending order, and no further computation is needed beyond calculating their difference. This demonstrates the adaptability of the algorithm to different input sizes and configurations while maintaining efficiency and correctness. This solution implements the minimum absolute difference problem efficiently. We start by sorting the input array to ensure that elements are in ascending order. Sorting guarantees that the smallest difference can be found between consecutive elements of the sorted array. We initialize min_diff to infinity to track the smallest difference encountered and result as an empty list to store the pairs with this difference. We then iterate through the sorted array, calculating the difference between each consecutive pair of elements. If the current difference is smaller than min_diff, we update min_diff to this new value and reset result to store only the current pair. If the difference equals min_diff, we append the current pair to result. Finally, we return result, which contains all pairs with the minimum absolute difference. The algorithm's time complexity is dominated by the sorting step, making it n log n, where n is the length of the input array. This approach is efficient and handles all edge cases, including arrays with duplicate values or very large ranges of integers. Here, we start by importing the necessary utilities from Java and defining the solution class. The method minimum_abs_difference takes an integer array as input and will return a list of pairs with the minimum absolute difference. The first step is to sort the array using arrays.sort, arr. Sorting ensures that all elements are in ascending order, which simplifies the process of finding consecutive pairs with the smallest difference. Next, we initialize two variables, min_diff, which is set to the maximum possible integer value, and result, which is an empty list to store the pairs that have the minimum difference. The core logic begins with a loop that iterates through the sorted array, starting from the second element. For each pair of consecutive elements, we calculate their difference and store it in the variable diff. If this newly calculated difference is smaller than min_diff, we update min_diff to this new value, clear the result list, and add the current pair to the list. This ensures that only pairs with the smallest difference are stored. If the difference equals the current min_diff, we simply add the current pair to the result list without clearing it, as it matches the smallest difference found so far. Finally, after completing the iteration through the array, we move to the last step, which is to return the result list. This list contains all pairs of integers with the minimum absolute difference found in the array. The implementation is efficient because sorting the array ensures that we only need to check consecutive elements for differences, and by keeping track of the smallest difference throughout the loop, we avoid unnecessary computations. The method ensures that the output is accurate and contains all valid pairs, making it a concise and effective solution to the problem. In this problem, we are tasked with finding all pairs of elements in the array that have the smallest absolute difference between them. Let's start with the first example, where the input array is 4, 2, 1, 3. The first step is to sort the array, so that the elements are arranged in ascending order. Sorting makes it easier to calculate the absolute differences between consecutive elements, which is critical for this solution. After sorting, the array becomes 1, 2, 3, 4. Next, we initialize two variables, min_diff, which we set to infinity initially, as this will eventually hold the smallest absolute difference we find, and result, an empty list that will store the pairs of elements with the smallest absolute difference. These initializations set up our solution framework. Now, we iterate through the sorted array to compute the absolute differences between consecutive elements. For the first pair, the difference between 2 and 1 is 1. Since 1 is smaller than infinity, we update min_diff to 1 and initialize our result list with the pair 1, 2. For the next pair, the difference between 3 and 2 is also 1. Since this is equal to the current min_diff, we append the pair 2, 3 to our result list. Similarly, for the final pair, the difference between 4 and 3 is again 1, so we append 3, 4 to the result. At the end of this process, our result list contains all pairs with the smallest absolute difference, which is 1, 2, 2, 3, 3, 4. This is the final output for this example. Let's consider the second example, where the input array is 1, 3, 6, 10, 15. The first step is to sort the array. In this case, the array is already sorted, so no changes are needed, and it remains 1, 3, 6, 10, 15. Next, we initialize the same two variables as before, min_diff, set to infinity, and result, an empty list. These initializations prepare us to calculate the smallest absolute difference and store the corresponding pairs. We now calculate the absolute differences between consecutive elements in the sorted array. First, the difference between 3 and 1 is 2. Since 2 is smaller than infinity, we update min_diff to 2 and add the pair 1, 3 to our result list. Next, the difference between 6 and 3 is 3. Since 3 is larger than the current min_diff, we make no changes. Similarly, for the difference between 10 and 6, which is 4, and between 15 and 10, which is 5, both are greater than min_diff, so no updates are made. At the end of the iteration, the only pair with the smallest absolute difference is 1, 3, and this becomes our final result for the second example. In the third example, the input array is 3, 8, -10, 23, 19, -4, -14, 27. The first step is to sort the array, which rearranges the elements in ascending order. After sorting, the array becomes -14, -10, -4, 3, 8, 19, 23, 27. Once again, we initialize the variables min_diff as infinity and result as an empty list. These steps allow us to proceed with finding the smallest absolute difference and the corresponding pairs. Next, we calculate the absolute differences between consecutive elements in the sorted array. The difference between -10 and -14 is 4. Since 4 is smaller than infinity, we update min_diff to 4 and add the pair -14 -10 to our result list. The difference between -4 and -10 is 6, which is larger than min_diff, so no changes are made. Similarly, the differences for the pairs 3 and -4, which is 7, 8 and 3, which is 5, and 19 and 8, which is 11, are all greater than min_diff, so no updates occur. The difference between 23 and 19 is 4, which equals min_diff, so we append the pair 19, 23 to our result list. Finally, the difference between 27 and 23 is also 4, so we append 23, 27 to the result list. At the end of this process, the final result is -14, -10, 19, 23, 23, 27, which contains all pairs with the smallest absolute difference. The time complexity of our solution is O, n log n, and to understand this, we can break it down step by step. First, sorting the array using the built-in sort method takes O, n log n, time. This is because the sorting algorithm, timsort, operates at that complexity for an array of length n, and this is the most computationally expensive part of the solution. Next, we iterate through the sorted array to calculate the absolute differences between consecutive elements. This iteration involves n1 steps, which is a linear operation that takes O, n, time. Lastly, whenever a smaller difference is found, we clear and update the result list. Appending to the result list is an O(1) operation, and since this can happen at most n1 times in the worst case, this contributes O(n) to the total complexity. When we combine these steps, the sorting step dominates the overall time complexity, making it O(n log n), while the linear iteration step adds O(n), which is relatively insignificant in comparison. Now let's analyze the space complexity, which is O(n). First, sorting the array using Python's timsort algorithm is done in place, but it does require additional space for temporary arrays. In the worst case, this auxiliary space usage is O(n). Next, we have the result list, which stores pairs of elements with the minimum absolute difference. In the worst case, if all adjacent pairs in the sorted array have the same minimum difference, the result list could store up to n/2 pairs, where each pair consists of 2 elements. This means that the result list requires O(n) space. Finally, other variables such as min_diff, diff, and the iteration index only require constant space, or O(1). When we combine these components, the dominant factor is the space used for sorting in the result list, making the overall space complexity O(n). Let's compare this optimized approach to a brute force solution. In the naive approach, we would calculate the absolute difference for all possible pairs of elements in the array. This involves iterating over all pairs I, j, where 0 less than or equal to I less than j less than n, calculating the absolute difference for each pair, and updating the result list based on the minimum difference found. The time complexity for this approach is O(n squared, because we need to check all pairs, and the space complexity is O(n) for the result list, which stores the minimum difference pairs. In contrast, the optimized approach significantly improves time complexity to O(n log n by leveraging sorting and a single linear traversal to find the minimum differences. Both approaches require O(n) space for the result list, but the optimized approach is much faster for larger arrays due to the reduced computational overhead. This makes it far more practical for real-world applications. Now let's break down the best, average, and worst-case scenarios for this solution. In the best case, the array is already sorted. Even in this scenario, the sorting step still takes O(n log n, because the sorting algorithm doesn't assume the input is sorted. The subsequent linear iteration step takes O(n, so the total complexity remains O(n log n). For the average case, where the array is randomly ordered, sorting continues to dominate the complexity, contributing O(n log n, and the iteration step remains O(n). The overall complexity is still O(n log n). In the worst case, the array is in descending order, requiring a full sorting operation. Even in this scenario, the time complexity remains O(n log n for sorting in O(n) for the iteration step, with the total time complexity dominated by the higher order term, O(n log n). Space complexity across all cases remains O(n), combining the auxiliary space used by timsort and the space for the result list. This reinforces that our optimized solution is efficient and consistent across all scenarios. When approaching problems that involve minimizing or comparing differences, one common mistake is neglecting to sort the array beforehand. Sorting is often a crucial first step, as it can highlight patterns and simplify the logic for an optimized solution. Without sorting, you may end up with inefficient or incorrect results. Another frequent pitfall is overlooking edge cases. For example, arrays with only one or two elements, such as 5 or 5, 5, require special handling. Similarly, mixed inputs involving negative numbers or duplicates can lead to unexpected behavior if not accounted for. Additionally, relying on nested loops to check all possible pairs can result in n squared time complexity, which is impractical for large inputs. Instead, more efficient algorithms, like sorting or hash maps, should be used. Lastly, misunderstanding the problem statement can lead to errors. For instance, failing to distinguish whether pairs like A, B, and B, A are considered the same or whether duplicates are allowed can result in incorrect solutions. It's always important to carefully interpret the constraints before coding your approach. Another consideration is integer overflow, which can arise in some languages like Java or C++ when working with very large integers. For example, calculating abs, a(b) for values where a and b exceed 10 to the power of 9 may produce unintended results. Using appropriate data types, such as long in Java, helps avoid this issue. Beyond these technical details, there are key insights that can help during interviews. Recognizing patterns is critical. Problems involving pairwise differences, sums, or products can often be tackled efficiently by sorting the array or leveraging hash maps for constant time lookups. It's also important to weigh the trade-offs between time and space efficiency. For instance, sorting provides an n log n solution, but a hash map might offer n time complexity at the expense of additional space. Clear communication is vital during interviews. Explain why you chose a specific approach, like opting for sorting to minimize comparisons. Finally, never hesitate to ask clarifying questions, such as whether duplicates are allowed in pairs or if the input array can be modified. This ensures your solution aligns with the problem's constraints. To further enhance your problem-solving skills, you can explore related problems that build on similar concepts. For example, LeetCode 1.2 sum focuses on finding pairs with a specific sum, while LeetCode 15.3 sum extends this idea to triplets. LeetCode 5.32 kdiff pairs in an array directly involves finding pairwise differences, and LeetCode 16.3 sum closest introduces the challenge of minimizing the difference to a target sum. These problems provide valuable practice and reinforce the strategies we've discussed. In terms of alternative approaches, sorting the array followed by a two-pointer technique is a popular and efficient method. This combines the n log n complexity of sorting with an n traversal, making it highly effective for a wide range of scenarios. Another option is the hash map approach, which leverages constant time lookups to achieve n complexity in some cases, though it does require extra space. For sorted arrays, binary search is another powerful tool for efficiently locating matching pairs when the target difference or sum is fixed. Finally, the sliding window technique is a versatile approach, particularly for problems involving continuous subarrays or ranges. By dynamically adjusting the window size, this method avoids unnecessary comparisons and achieves n time complexity. It's especially useful in scenarios where you're working with ranges of values or looking for specific patterns within subsets of the array. Mastering these techniques and understanding when to apply them will greatly enhance your problem-solving toolkit, making you more efficient and effective in tackling a variety of coding challenges. Great job! We've successfully solved the minimum absolute difference problem. To summarize, we used sorting to simplify the process and achieved an efficient solution with n log n time complexity. Remember to practice similar problems to strengthen your understanding of array manipulation and sorting techniques. Thank you for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!